let's start. So I want to prove the faithfully flat descent for quasi-coherent sheaves. So we have the following theorem. Okay. Yeah. So let U be a covariant sieve for f on x for f PQC topology. Then, so we have two categories. We have the category of quasi-coherent sheaves on X, and we have the category of quasi-coherent sheaves on this covariant sieve. And we have a functor. Let me give it pi, let's call it pi upper star. And the claim is that this is an equivalence. So, so informally, I will not recall definition of this category in general, although I will recall it in the case of affine schemes in a second along the proof. But informally, so what you do, you sort of you have a FPQS cover, so it generates a covariant sieve, and you look at the categories of quasi-coherent sheaves on all objects of this covariant sieve, and you take its limit of categories. So for every object of U, you have a quasi-coherent sheaf. For every morphism in U, you have isomorphism between the pullback and the sheaf that, and well, you have compatibilities. So, slogan here is that the rule that assigns to every scheme X the category of quasi-coherent sheaves is a sheaf and in FPQC topology. So we defined what is a sheaf of sets, a sheaf of abelian groups on a site, and I recall that the condition was that global sections of a sheaf on X is the same as locally given sections. So for any covariant sieve of X, you have the set of locally given sections, and global sections must be isomorphic to this. And with some efforts, you can generalize this, kind of go up one categorical level. You can talk about sheaves of categories. And then, so it requires some paperwork. So if this definition is set up, then this is a good example. That's precisely what it means, that category of quasi-coherent sheaves is a sheaf on, again, the rule that assigns to every X the category of quasi-coherent sheaves is a sheaf in FPQC topology. Okay, so, and well, I recall that at least for sheaf of sets or for sheaf of abelian groups, saying that a pre-sheaf is a sheaf for FPQC topology is equivalent to saying that it's a Zariski sheaf and it satisfies certain descent for morphism of affine schemes. So the proof, well, so step one of the proof is the following. Reduce to the case when X is affine, spec A, and U is generated by a single faithfully flat cover, flat surjective morphism from spec B to spec A. So explicitly, our U consists of all schemes over spec A that such that this morphism factors, not uniquely, through spec B. Okay? So, and once again, so if we talked about the sheaves of sets, then, presheaves of sets, checking that it's a sheaf is equivalent to checking that it's a sheaf for this particular sheaves, and it's also a sheaf for the risky topology. So assume that we know that category of that quasi-coherent sheaves can be glued along open cover of X, the risky open cover. So it's OK for the risky topology. So therefore, at least it's reasonable to assume that this condition is it's enough to check this. And again, the proof, the reduction, the step one is formal and boring. So I will omit details here.
Formal, but don't we have to know first that morphisms move in every topology in order to fulfill this step?
No, again, so you don't need to know anything.
If you wish to verify that something is a stack, you have two things. First, you have to check that morphisms move in this topology, and then you have to show that objects move. And you're just
Well, so morphisms, you need to check that morphisms maybe also form a sheaf for FPQC topology, and this itself it suffices to verify this for the risky topology and for covers of this type. Okay, so now let's see explicitly what it means. So step two, okay, so how I want to phrase this, before so step two, so, and this is, so is the following. So theorem is, is true. Theorem is true if this morphism spec B from spec B to spec A admits a section. Okay? So why that? In this case, U, what is U? So suppose you have, let's consider the sieve generated by any map that admits a section. What is U in this case? Everything, right? Every morphism from U to spec A factors through spec B. How you can construct this? Well, how you construct this dotted arrow? So you have spec B, you have spec, yeah, so I claim that this is everything, just the category of schemes over A, over spec A. And so here is the reason why it's true. So suppose you have any object of this category. So you have a scheme. So you want to show that it factors. And you have a section. And you simply compose, you define this dotted arrow to be the composition of this map and the section. Good. So in this case, our U has a final object. And in particular, this category here is just equivalent to the category of quasi-coherent sheaves on X, right? It's a limit of categories of quasi-coherent sheaves on all U. So if you have so spec A is the identity morphism from spec A to itself belongs to this sieve, right? So spec A identity to spec A is an object of U. And therefore, well, you have a quasi-coherent sheaf on spec A assigned to this object. And by the very definition, so the sheaf assigned to every U is the pullback of that. So, and now we are going to reduce the general case to the case when we do have a section. And this is the main trick. It's, okay. So I will need a lemma. So step 3, it's a lemma in commutative algebra. So we are talking here about faithfully flat map of affine schemes, so that's about properties of faithfully flat morphisms. So, so assume that morphism from spec B to spec A is flat and surjective. So B is flat A algebra. Then two assertions. A sequence of A modules, say M1, M2, M3, is exact if and only if the sequence obtained by tensoring with B over A is exact. No, so for us, faithfully flat means that it's flat and surjective. So, so this is an easy statement, and for the proof of that particular theorem, that's all we need. But this equivalence has some. We will later use some extra properties of this equivalence of categories. For example, we will need to know that vector bundles here under this equivalence go to vector bundles here. And so this requires an additional statement. So, so I claim that the tensor product with B preserves some class of modules. So M is a finite well, A modules, or also it's true for finitely presented, locally free of finite rank if and only if M tensor B over A is finite A module. Is a finite. Finite means that it's finitely generated. B module. And the same is true for all other properties. So all properties are preserved. А почему?
Ну, потому что можно конечно порожденность переписать.
Да, ну почти. Доказательства все в одну строчку. Okay, so let's. Do I have? Yeah, I have another blackboard here. So let's see what we have to prove. Well, I should say that this is a very important theorem, and not only its statement, but also the proof is very kind of conceptual, very short. So I recommend to kind of understand all the details, at least here. Well, I omitted a part which I decided is kind of is technical and tedious, but so that's really the heart of the proof. So, okay, so proof. Well, so in one direction it's obvious. So this is okay because since tensor product over A with B is exact. And now, so you want to show that the inverse direction. So you want to show that if this is exact, then this is exact. So exactness means that cohomology of this complex is equal to the cohomology of this complex tensored with B over A, right? So I need to know that if cohomology here is trivial, then the same is true here. So, and for this, it's enough to show that if M tensor B over A is 0, then M is 0. So if you have an exact and conservative functor, conservative means this, then so sequence is exact if and only if its image under this, my functor, is exact. So assume not if m is not 0, then there exists a submodule of the form A mod A in M, right? You take any non-zero element, and it's and this is non-zero, да. Okay. Good. So now, so because my functor is now M, if M tensor B over A is 0, then the same is true for A mod A tensor B over A. Because, again, the functor is exact. So if this were non-zero, you would get an injection from a non-zero module, namely this one, to 0 module. So by exactness. So that means that B mod A is 0, but I claim that this contradicts to the surjectivity of the map from spec A to spec B, from spec B to spec A. Okay, so let's take, let's consider spec of B to spec of A. So here I have, this is surjective, let's call it pi, and here I have the closed subset given by the 0 locus of A. So that consists of all ideals, prime ideals that contain A, right? Yes. Yes. Да, абсолютно верно. Я глупость сказал. Okay, so A here is thank you very much. So is an ideal. Thank you. For some ideal. It doesn't matter. Ideal A. Okay, so you just take a non-zero element and you take its annihilator, which is an ideal, and it's not everything. So this is non-zero. So okay, so you take an ideal and you take the closed subset given by this ideal, and now here you have, this is non-empty, and it follows that from surjectivity that pi inverse of ideal AB, pi inverse of VA is also non-empty, and this is V of AB. And this is non-empty. Okay? And this is contradiction. So we know that this is this ideal is not everything. On the other hand, the quotient is 0. Okay? Good, thank you. Now, let's prove the second assertion. Well, let's observe that if you have any collection of elements, finite collection of elements in M tensor B over A, then there exists. So what we want to prove, of course, in one direction that's obvious. So if M is finitely generated, that M tensor B is finitely generated. So we want to show that if this is finitely generated, that M is finitely generated. So suppose you have any collection of elements, then there exists a finite submodule such that x1, all these elements belong to M prime tensor B over A in M tensor B over A. Right? Because by definition of tensor product, you write this as a combination of tensors and look at the submodule generated by all the coefficients. So if x1, now if x1, xn generate M tensor B over A, then so this M prime tensor B over A must be equal to M tensor B over A, right? Because generators belong. And now we have the conservativity, so M prime is a submodule of M, and the tensor product with B are equal. So by exactness and the conservativity, we conclude that M prime is equal to M. Okay? So this is one assertion. Now, so let's prove again the fact that if M is finitely presented, then so by definition, a module is finitely presented if it's isomorphic to the co-kernel of map between three modules of finite rank. Okay, so let's choose finite presentation. Choose okay, so we want to show that let's take B and choose finite presentation. So choose any surjection from a free module of finite rank to M tensor B over A. Then it's so whenever so I assume that this is finitely presented. Then for any surjection from a free module of finite rank, this guy is also going to be this kernel N is going to be a finite type. Is of finite type. Sorry. N is finite. Sorry, maybe I should. Yeah, sorry. Let's do it better. So let's write this. So again, I need to show that if this is a finite presentation, then M is a finite presentation. But well, in particular, we assume that this is a finite module. So so choose a map from AN to M. And let's let N be its kernel. Okay, I know that it exists. And we will be done if we show that N is finite. So want N is finite. Okay, so we tensor it by M. We get a surjection. And now I'm going to use the following fact that if you have a finitely presented module and any surjection from a free module of finite rank, so if this is a finite presentation, this is finite, then this is finite. This is an elementary statement. So this implies that N tensor B over A is finite. And this implies that N is finite. So by definition of finite presentation, so a module is a finite presentation if there exists a surjection like this, such that the kernel is finite. But the claim is that once you know this for one surjection, it's also true for all surjections. There is something to check here, but it's not hard. So N is finite, and then we are done. So for the last assertion, so maybe let's say this is A, this is B, and for C, well, so there is a characterization of locally free modules of finite type. So locally free of finite rank modules is the same as flat and of finite presentation. Well, I didn't know that fact, actually. So it's a classical fact that if you have a Noetherian ring, then any finitely generated flat module is locally free. So the proof uses Nakayama lemma. So you choose a maximal ideal, you choose the generators of your module modulo the maximal ideal, and then you leave them to set of elements in them, and then you show that locally it's a basis. So it requires that a submodule of a surjection from a free module to your module has finite type. And finite presentation precisely guarantees you. In a Noetherian case, this is automatic. It follows just from finite type condition. In non-Noetherian case, you need finite presentation. But the proof is literally the same as in the Noetherian case when you only have finite type condition.
Or can you just say that if something is finite presentation, that is the base change of a module over an algebra of finite type over C, and that we know this?
Okay. Yeah. So, so now it's, I need to show that flatness and well, finite presentation is not only preserved, it's kind of invariant under the base change, and flatness is also invariant, right? So I claim that if M tensor B is flat, then M is flat. Is it obvious? So all we need to check is that
Is there a reason you didn't use projective instead of local free? Is there a subtle difference in the Noetherian case?
projective and locally free.
Because it's usually stated for finitely.
Well, you have a quasi-compactness. It's OK, yeah. So you can say projective. So OK. So if M, well, it remains to show that if that's what we want, that if M tensor B over A is flat, then M is flat. Well, so you have an exact sequence, N2, N3. It's exact. And so you want to show that this sequence is exact. N2, M over A, N3. OK, so what is the idea? The idea is to, so we want to show that check the exactness of this sequence. It's a sequence of A modules. And it's exact by the first assertion if and only if its tensor product with B over A is exact. So this is exact. So why it's exact? So because we assume that this guy is flat. And now you can, this is a tensor product over A. And you can So assume that this is exact. Now, I claim that then this sequence is exact. Why it's exact? Because I can first, so this is a B module, so I can first take this sequence N1, N2, N3, this one, and tensor it with B. I still get an exact sequence. And then this sequence is obtained by tensoring product, by taking the tensor product with this flat module, with this flat B module over B. So this is exact. And it implies that this is exact. Right? Because tensor product with B does not change. Exactness. Good. So we check that if M tensor B is flat, then M is flat. And this completes the proof. Well, now, so we have this lemma. Let's use it. So the last step. So I want to reduce the proof to the case when the morphism from spec B to spec A has a section. Well, so step 4. Okay, so let's recall definition of the category of quasi-coherent sheaves on this covering sieve. So I explained last time this explicitly what it means, so I will recall it. We have X, which is our spec A. We have U, which is spec B. And here we have two maps from U times U over X. And this is, and here I have three maps from U times U times U over X. And this category can be described in terms of this diagram as follows. So, what it means by definition to give an object here? It means that we have a quasi-coherent sheaf on U, so a B module, plus we have an isomorphism, P1 upper star Fu. Well, so we have also F U times U over X, right? By definition of this category, for every scheme that admits X scheme, such that the morphism from this scheme to X factors through U, I have a quasi-coherent sheaf, and we have isomorphisms. So Fu. So, and in particular, so this Fu has the property that when I pull it back to U times U over X, I get an isomorphism. Let's call it phi. And last time, we described this category quasi-coherent sheaves. Let me write it here. So as the category of pairs Fu and together with this isomorphism P1 upper star Fu and P2 upper star Fu, which is called the descent atom phi, such that this phi satisfies certain co-cycle condition. So what is this co-cycle condition? So I formulated last time such that the following diagram is commutative. So I take this scheme here, and it has 3 maps to U, 3 projections. So I can take P0, P1 upper star. Sorry, my P is, stands for 2 things. So for these projections and also for these projections. So I have P1 and P3. So now we are talking about, these are sheaves here. And phi defines an isomorphism between these 2 sheaves. Namely, I can simply consider the map from here to here, which discard the middle coordinate. So this is P1, 3, upper star phi. It defines an isomorphism. Or, equivalently, I can consider, construct an isomorphism between these 2 sheaves in a different way. I can go through P2 upper star F. And there are 2 isomorphisms here, which is P1 to upper star phi, and similarly here. And the condition is that this diagram is commutative. Okay? So explicitly, this category can be described as the category of pairs with this property. So, okay, some notations. So I will, so this is a quasi-coherent sheaf on affine scheme. So it corresponds to some, it corresponds to a module. So M prime is a B module. M prime is a B module. And tilde means for the functor from modules to quasi-coherent sheaves, sheafification. And so I also have this, and I will call it M double prime tilde. And M double prime tilde is a B tensor B module. Yeah, so, okay, good. So my goal is to show that the category of quasi-coherent sheaves on X is equivalent to the category of quasi-coherent sheaves on this U under the pullback functor that I denoted by a pi upper star. So explicitly, if you have a quasi-coherent module F here, then this guy, this functor, it sends a quasi-coherent module F to its pullback under the morphism from U to X. Yeah, so this is U, this is X, this is pi, and this is the functor. And so this is Fu, and it comes with the obvious descent atom. So, so I want to show that this is an equivalence, and in order to do this, we'll construct a right adjoint functor. So right pi low star, and it will be right adjoint. So I have an object of that category. It can be described either in terms of that diagram or in terms of this M and M prime and M double prime. And let's think what could be the right adjoint. How can we produce an A module from this? So, okay. So suppose I have an object of this category. So I have M prime again, which is just global section of FU, global sections on U of FU, and I have global M double prime, which is global sections on U times U over X of F U times U over X. And, well, this guy can be either identified with pullback with respect to the first projection or with the pullback with respect to the second projection. And this gives me two errors. Right? So if I have a section of F sub U, it gives me a section of the pullback. And therefore, it gives me a section here. Yes? Or equivalent, well, another construction is that if I have a section here, I can construct, so there is a map from gamma U F U to gamma U times U over X of Pi. I is either 1 or 2 of FU. And this is di. So I have d1 and d2. These two maps are given by this obvious pullback maps on sections. So any object here gives rise to two modules. This is M prime is a module over B, and this is a module over B tensor B. So of course this is you can't say that these are morphism of B modules. This is not a B module, but well, this is a homomorphism. This is a diagram where B goes to B tensor B over A. I also have here two maps, D1 and D2. One map takes an element B and sends it to B tensor 1. Another map takes an element B and sends it to 1 tensor B. So you see, you have a diagram of rings, and this is a diagram of modules over these rings. And I claim that it's compatible in the obvious way. So for example, this guy is a morphism of B modules, where the B module structure here comes from this D1, and similarly here. Okay? So again, an object here produces a diagram like this. And now, so I will define an adjoint functor pi rho star of F. So an object there is, this is a name for the object in that category of quasi-coherent shifts on U. is going to be there. Well, you take these two maps, D1 and D2. You take their equalizer, so the set of elements here, the group of elements here, such that the two images are the same. This gives you an A module, right? Because, so A maps here, well, it actually sits here because it's flat. So, and by definition, D1 of every element of A is equal to D2 of the same element. So that means that this equalizer is an A module. And since it's an A module, I can construct a quasi-coherent sheaf on X by applying this tilde factor. So I claim that this is an adjoint functor. How you check that the two functors are adjoint? Well, so a convenient way of checking that two functors are adjoint is by constructing what's called unit of adjunction and co-unit. So, we need map from pi upper star, pi lower star to identity. That's called the co-unit. We also need a map from the identity to pi lower star to pi upper star, such that two conditions hold. So the conditions are the following. So suppose you have two functors and these two arrows. Then you can construct a map from pi lower star to, well, applying the unit to pi lower star, pi upper star, composed with pi lower star, right? So you take this unit times identity, and now you use associativity and co-unit to map it to pi lower star. So two functors are adjoint, and similarly, you can construct a map from pi upper star to, you use, again, unit, so pi upper star times pi lower star, pi upper star, and then map to pi upper star. So two functors are adjoint if you have these two arrows such that the composition are identity maps. That's a very nice definition of adjunction. So let's construct this. So what do we mean? What does it mean to? So here I start with any m prime, and so I take equalizer of map from m prime to m double prime. This is an A module, and I tensor it with B. And so this gives me a B module, and I want to show that it's, so I want to map it to M prime. Well, the map should be compatible with the descent datum. So first of all, I need to map it to M prime. So how to map it to M prime? Well, this is a submodule of M prime. A submodule. So you just, this is the product map. So it's, by construction, it's compatible. So this is an A module. So this tensor product comes with the descent datum. And by the very construction, this map that I defined, that product map, is compatible with this descent datum. This is one. This is co-unit of the adjunction. Now the unit of the adjunction. So here I have M. I have A module, and I'm supposed to apply pi upper star to this. Yeah, this is M. So, and here I take M. I tensor it with B over A. And so this should come with the descent datum. So there should be two maps from here to M tensor B times B over A over A. So the descent datum are just given by maps. There's an identity on M, and given by maps that takes B to B tensor 1 and 1 tensor B. These are the two maps. And what you need is a map from M to the equalizer of these two arrows. This must be the unit of the adjunction. This will be the unit of the adjunction. Well, and the map is obvious. It just takes an element x of M to x tensor 1. And I will leave it for you to check that these two conditions hold, that these two maps are identity. It's formal. OK? So this gives the adjoint functor. Now, what we want, step 5, we want to show that the two arrows, pi upper star, pi lower star, of these two maps, and from identity to pi lower star, pi upper star, that these two maps are isomorphisms. And that's what you want. So this is a very explicit statement. It's still non-trivial, because why it's non-trivial? So this pi lower star, well, it's given by this equalizer. How do you know that it's non-zero? You take something, M prime is non-zero, but how do you know that this guy is big? The second one is easier, right? But the first one is not. And the idea is to use the lemma that we proved in step 3. So we want to show, for example, here, we want to show that a certain map of B modules is an isomorphism. And it suffices to prove this after a faithfully flat base change. So by lemma, it suffices to prove this after a faithfully flat base change. A goes to some C. OK, so what I mean here, suppose we can find an algebra C over A such that this map is faithfully flat. So the map on spectrum is surjective and flat. Then using the lemma, it's enough to check that this map these two arrows are isomorphism after tensoring product, after taking the tensor product with C over A. Well, I can take over A. Then still I can take the tensor product over A. Or I can make a C into a B module by tensoring it first with B. Okay, so here is a diagram here. Что?
У нас сформулировали скоро в терминах модуля.
Да.
У нас там есть два этих отображения.
Да.
У нас есть какое-то условие концикла? Там?
Да, да, есть. Есть. Я его сформулировал, вот там была такое, некоторая коммутативная диаграмма была. Что? Да. Да. Данные это вот это m и m прайм, и m штрихом с двумя штрихами, с двумя отображениями, но эти данные должны удовлетворять некоторым условиям. Одно из условий, что m2 штриха, получается, каждое из этих отображений задает изоморфизм между m2 штрихами и m штрихом тензор B. Ну да. Но есть еще одно условие на этот изоморфизм. Одно единственное. Okay, so okay, so here is a picture. So you have, let's call this, so C, let's say Y is spec C. So I have my category of quasi-coherent sheaves on X. So here I have pi upper star, pi lower star. I want to show that they are mutually inverse functors. And so the idea is to consider the map, the pullback map. So my y goes to x, or maybe, sorry, let's say u goes to x. This is and this is y. And here I have u times y over x. So this gives me, this arrow gives me an exact conservative functor. And this covariant sieve gives me the category here, u times y over x. This is the covariant sieve generated by this FPQC cover. And I also have here two adjoint functors and this diagram. So I claim that this diagram is commutative. It's commutative in the following sense. So this diagram is commutative, and also this diagram is commutative. And this functor, these two functors are conservative. So what we want to show is that, for example, that this is an isomorphism. That's a map of two quasi-coherent sheaves on X. And I want to show that it's an isomorphism. It suffices to prove that it's an isomorphism here, right? Because of the conservativity. But the maps here are, again, units and co-units of the adjunction, of this adjunction. So now take C equal to B. So then So what we have is we have u mapping to x. We have our base change is our y is this u. So the fiber product is u times u over x, right? So as I explained here, it suffices to prove the theorem for this FPQC cover. But this cover has a section. And we are done. Okay?
Why did we need the fact that y upper star and y lower star are equal? It seems that we just constructed the factor and proves that this factor is universal.
Yes. Well, so we don't use this fact explicitly, though what we need is only the commutativity of this diagram. And so how you check the commutativity of this diagram? Well, one way to check this would be the following. So sort of you take this pilo. So okay, so yeah, you're absolutely right. So we don't strictly speaking use, but it must be a natural factor. Otherwise, it would be hard to check commutativity.
You know, it is a factor, but then they're reduced to show a certain level.
Yeah. Yes. Okay. So let's derive some corollaries. Well, so we proved an equivalence of categories. In particular, we have so that means that we have isomorphism. We have a bijection between isomorphism classes of objects, and we also have isomorphism on morphisms. So let's explore this, what it means. So I will formulate it as so corollary. Suppose you have a quasi-coherent sheaf on X. Let's consider for any scheme U over X, that's object of category of schemes over X. Let's consider a pre-sheaf on this category that takes any U to F, let's say F, to global sections over U of F low upper star of F. And I claim that it's a sheaf. On category of schemes over U over X with F, P, Q, C topology. Abusing notation, I will call this, well, sheaf, pre-sheaf, also F. So any quasi-coherent sheaf on X, for example, think of structure sheaf. Just F is a structure sheaf, OX. Then for any scheme, I can consider, for any scheme U, I can consider global functions on U. And I claim that it's a sheaf in FPQC topology. That's a very good example. Okay, so let's see why it's a corollary. Proof. So what we need to check? We need to check that locally given sections are the same as globally given sections. So so I need to check that. So let y be, so here is what we need to check. So suppose I have any object of schemes of the category of schemes over X, U, cover and sieve on Y, and then we need to check that global sections of F on Y. Recall that by definition, you take this F, you pull it back to Y, and then you take global sections on Y, is the same as locally given sections, F of U. Okay? So of course, so that's what we need to check. And when proving this, we may assume that Y is equal to X, because otherwise, we replace F by its pullback to Y. So we may assume that Y is X. And so then I claim that F of X is morphisms in the category of quasi-coherent sheaves on X from OX to F, right? So morphism from X to F is precisely global sections. You look where one goes. It determines the morphism. And now F U is morphisms in the category that we discussed in the theorem. In this category, from the same two objects, from OX. So OX is an element here, but in particular, it's an element here, and also F.
We don't know that F is sheaf yet, so we can't.
What do you mean? I don't know. Well, I think of F as an object of this category. I may consider, can view F as an object of this category. I know that the categories are equivalent, but there is obviously a functor.
You're saying that F is a locally given quasi-coherent sheaf.
It's given globally given. In particular, it's locally given. Yeah. So, and we just proved that this map is an isomorphism. So this gives me that this map is an isomorphism. Well, so if you sort of a bit unhappy with, if you're unhappy with this argument, so you can kind of trace back where we actually proved it, this particular assertion in our argument. So that's we reduce first to a fine situation, and then this statement is equivalent to the following, that if you have any module M, then you take locally given sections, which is nothing else but this equalizer of these two arrows, B tensor B, over A over A. So the two maps are given by two maps from B to B tensor B, B tensor 1, 1 tensor B. And you can take equalizer. And this assertion in the affine case, when U is generated by a single FPQC cover from an affine scheme, is an isomorphism. Okay? That's equivalent. That's what we proved. Okay, so and the last corollary, well, I want to finish by a theorem. So theorem here, and it's called faithfully flat descent for morphisms. Okay? So let's consider that's the following assertion. For any scheme X over some base S, let's consider the presheaf represented by X. So Y in schemes over S goes to morphisms over S from Y to X as a sheaf. On schemes over S with FPQC topology. Okay? So here is a corollary. So what does it mean? Suppose you have some Y, and suppose you have FPQC cover, and you have X, and suppose you have this map such that the two compositions are equal. And this is FPQC cover. Then there exists a unique map from Y to X, which makes the diagram commutative. That's precisely what it means. Well, for the particular sieve generated by a single FPQC cover. Right? So I will not give a, so the proof consists of two steps. One is reduction to the affine case, which is boring but tedious, and the proof in the affine case. So proof in for X and S affine. Well, so given a map, so say X is spec B, S spec A. So what are maps, morphisms from Y to X over S? These are algebra homomorphisms, morphisms in A algebras from B to global sections on Y of O Y, right? So for example, given a map to an affine space is equivalent to given a collection of global functions. And now the assertion follows, theorem follows from the fact that OR is a FPQC sheaf. So you can, what is an algebra homomorphism? So for every element of B, you're supposed to give yourself a function, but you can descend it with faithfully flat, with respect to the faithfully flat topology. So you can descend these algebra maps. Okay, I'll stop here. Questions?
So what we did is a couple last lectures. We defined sites, we defined sheaves on sites.
Yes.
And then we digressed to this. So what's our
our goal is to prove Veil conjectures. So, and in order to do this, we need to have tools for computing étale homology of various sheaves. So, for example, our immediate goal will be to prove that étale homology of the structure sheaf, or X, is the same as the Zariski homology of the structure sheaf. For example, higher homology vanishes for fine varieties. So, why it's right? So more generally, if you have a quasi-coherent sheaf on X, it defines a sheaf on even an FPQC side. So it defines an étale sheaf. And so it turns out that its higher homology is the same as Zariski homology. Да. And the descent for the étale topology for FPQC, for quasi-coherent sheaves, follows from this descent with respect to a stronger topology. So of course, I could suppress the discussion of FPQC completely, but so since the argument uses only this flatness and conservativity of the tensor product, so it would be kind of mass to, well, it's better to give an argument in general case.
So you wanted to have a category of quasi-coherent sheaves to be embedded into the category of the étale sheaves because it will help us to analyze.
For example, if you have a scheme in characteristic P, then you can imagine you have a map from OX to itself that takes a function f and sends it to f to the pth power minus f. And in characteristic P, this map of sheaves is surjective, and its kernel is Z mod PZ. So you have an exact sequence of sheaves. So knowing homology of this, and homology of this is just the Zariski homology of the structure sheaf. For example, they vanish for fine varieties, higher homology groups. You can derive some information from the long exact sequence about homology of this sheaf.
It's FPQC exact, but not
It's not Zariski exact because it's not true that Zariski locally you can solve equation f to the pth power minus f equal to g, but you can solve it nevertheless étale locally. So it's even étale exact, in particular FPQC exact.
So the embedding of quasi-coherent sheaves into étale sheaves is not.
Yes.
And also, I have a question before. So I think 2 lectures ago you mentioned a construction of representations of finite groups of Lie type in terms of.
Yes.
Yeah, so where can I sort of read?
So there is a very nice book. It's called Representation. I can send to you representation of SL2 over a finite field, where this theory of the linear lustig variety, its étale homology, this kind of Greenfield's curve, is developed in details. So it's kind of easy to read book. And I can send to you the book. But the theory in general is very kind of technically, well, there are many papers by Lustig. And there is a book by Lustig, which does not cover everything here. Well, doesn't cover kind of recent advances in this area. So this theory is called character sheaves. So his goal was to compute characters of complex, irreducible representations of finite groups of Lie type. And so along the way, he kind of described essentially all representations in homology, Edladi homology of certain algebraic varieties called the linealistic varieties. And so this helps him to do the computation. But again, so even the statements are not that easy to grasp.
So but there is, for SL2, it's written.
Yes, yes. Mm-hmm. And it's kind of, James. More questions? Да.
Я правильно понимаю, что та теорема, которую мы доказали, она работает для любой топологии, которая зажата между Зарийским и Faithfully Flat, для когерентных пучков?
Да, да, правильно. Да, в частности, для Италии, да.
Нам надо считать именно вот так, топологии,
Да, да. Вот на самом деле мы докажем, значит, утверждение про когомологии, которое, не совсем формально следует из того, что мы уже знаем. Значит, вот нам нужно будет доказать, что у когерентных, квазикогерентных пучков высшие когомологии, когомологии в плоской когомологии такие же, как когомологии Зарийского. Это почти идеологически это следует из того, что мы доказали. Технически не совсем. Вот. И после того, как мы это сделаем, мы забудем про плоскую топологию, мы извлечем из этого некоторые следствия про когомологии когерентных пучков в этальной топологии, а потом будем изучать кривые и докажем две главные теоремы о собственной замене базы и о плоской. Они аналогичны тем двум утверждениям, которые мы доказывали для фундаментальной группы. Там же они будут использоваться, утверждения про фундаментальные группы, в доказательстве. Вот эти вот про специализацию. Вот была такая теорема сложная. Мы ее докажем аналогичное утверждение для когомологии. Ну а дальше, значит, используя эти теоремы и вычисления для кривых, мы будем, значит, как-то докажем формулу Левшица, а потом, рассваивая на кривые, докажем оставшуюся гипотезу. Вот такой план. Спасибо.